Okay, so let's start the class. Last time we stopped here, and typical question, like a conceptual question. So you have two charges. One is stronger than the other one. Okay, one has 25 nanocoulomb. So nano is 10 to the negative 9. The other one is 15 coulomb. And so if you want to find the force between them, okay, we did that already. I'm not going to do it. You apply Coulomb's law. Okay, so the first thing you always do is to draw. Okay, so it says positive, so you will do positive here, positive here. You put a label, so that will be maybe number 1, that will be number 2. Okay, so you report everything here on a drawing. So maybe here it's going to be nanocoulomb here, and here it's going to be 25 nanocoulomb. Okay, so everything in a drawing here, and that will be 15 centimeters. So you convert that right away to meters. Once you have done that, you see that the force will be what? Do they repel or do they attract? Repel, very good. But we always look at only one. So I'm going to look at this one. It's going to be acted upon by a force. So that will be the force 2 on 1. So if it's a vector, it's going to be negative. For now, I want just the magnitude. So I'm not going to do the math, but just how to set up the equation. So 9 times 10 to the 9, okay, that will be your electric constant, times Q1, which is 15 times 10 to the negative 9, times Q2 times 10 to the negative 9. You have to be careful with your TI. You see, you frame here, you don't need to put a times, you frame, and then you frame, and then you frame. The TI understand that you are multiplying over here, and that will be the distance squared. Okay, so you can do that on your own. You don't. Oh, by the way, in the Dropbox, you have all the tutorials for all those problems. So if you need additional help, I've done the tutorials for every single problem, I think. But the question is, once you have found this force here, what's going to be the force on the other one? Is it going to be the same, or is it going to be larger, or is it going to be smaller? The same, very good. Okay, Newton's third law. So typical conceptual question, even for the MCAT, they will try to trick you. Okay, oh, this one has a larger charge, so sure enough, the force will be larger. No, the force is always the same because Newton's third law. Forces come in pair. For every action, you have an equal and opposite reaction. You cannot push harder than you are being pushed, and you cannot be pushed harder than you are pushing. It's the rule. Newton makes the rule. Okay. A lot of applications in biology. So we already talked about that. When you have an electric signal traveling along the neurons, for example, or the nervous system, it's not really charges moving. It's just a change in voltage that will propagate. So this is called the action potential. Okay, so we talk about that. I think we already talked about that. I have a better picture somewhere in another slide here. You see some, I think it's called an elephant fish. I think someone told me that. It's producing here an electric field. It looks like a dipole. This is because I don't know why. You can look it up how it works. I'm not sure. But this electric field can sense the environment around the fish. Maybe it has a poor eyesight. Maybe it's a muddy water, IDK. But for example, if there is a conducting material here, something that it can eat, like something living, okay, so that will be the living thing here, sorry. So that's like a calamar or something that is living. You see that the electric field here cannot penetrate inside. And the electric field here will go on the surface, so it will be polarized. One side will be plus, the other side will be minus, but it cannot penetrate. So it will increase the electric field here. If you have a not conducting stuff, so maybe a plant or a stone, You see the electric field here? It's going to be weakens. So it weakens the electric field. The electric field can go through it. If you want, after the class, I can explain why. But it's not going to react the same way with a conducting material and a not conducting material. So that's how the fish can detect whatever is in the environment. So this is do not eat, and this is do it. Okay, so a lot of applications here in biology. So we talk about that already. Okay, so let's talk about that. So remember from physics 1, the Earth, okay, is like making an aura around it. Okay, so we call that the gravitational field. So it's like an aura because it has some mass in such a way that if you put a mass here, so this is the moon, maybe there was the moon here, the moon smaller than the Earth. So then that mass here, okay, will interact with with the gravitational field, and there will be an attractive force, right? So there will be the force due to gravity. That's because the mass is placed in that gravitational field. That gravitational field exists even if you don't put a moon, or if you don't put people around, or if you don't put any mass inside that field, it still exists. And then you place a mass inside the gravitational field, and that mass, okay, will be acted upon by a force that we call mg. So this idea of field was introduced in the 19th century by Michael Faraday. Before that, Newton said that the Earth grabbed the moon instantaneously and pulled it toward it, right? So the moon wants to keep going in straight line at a constant speed. No, it can't. There's a force pulling in. Now you introduce the idea of a field, okay? So it's like an aura, and if you place a mass inside that field, it's gonna feel that field, and it's gonna react to it. Is that clear? So you see that field is toward the Earth. So if you put a mass here, okay, it will be acted upon by a force, the force due to gravity, and it's gonna follow the line here, and it's gonna accelerate. So here it has some potential energy that will turn into kinetic energy. So likewise, if you take a negative charge here, if you take a negative charge, also it's going to create an aura around it, okay, all around, in space around. And if you place a positive charge, you see, it will feel that aura, and it wants to go toward the negative charge, right? So it will accelerate. So let me ask you something. Um, do you remember the gravitational field? How do we used to call it? G, right? Gravitational field 9.8. It was the field, okay? The field on Earth is about constant, right? And what was the force with G? Gravity, the weight, huh? The mass, mg, right? The mass times the acceleration. So that acceleration, you can see this as an acceleration, okay? If you drop something, it's going to accelerate, but it's also the field, the gravitational field. So if you place a mass inside that gravitational field, it will be acted by a force equals to mass. Okay, so mg, okay? Do you agree? So likewise, if you have a source here of an electric field, so this is called the electric field, this is called the gravitational field. If I put a charge Q, okay, and the field is called, the electric field is E. So here I have G and now I have E. What do you think the force will be? E equals 2, if you build the analogy. So here the force is mg, here, instead of having a mass, I have a charge Q, so it's also a property of matter. And the field, we call that E. So the force will be QE. Excellent. Okay? So any source here, like a Van Graaff generator, okay, will produce an electric field around. And if you place a charge in that field, and this charge is small enough that it's not going to disturb the structure of the field, it will be acted upon by a force equals to PE. Are you with me? Okay, so close to the Earth, we have the gravitational field here equals to 9.8. If you place a mass, so 9.8 close to the Earth, and then if you move away from the Earth, is it going to be the same or it's going to be less? If you move away from the Earth, is your weight will be the same or your weight will be less? Less. Okay, so inverse square law. If you are one, so this is the Earth. If you are 400 pounds on the Earth, okay, at a distance r from the center of the Earth, you multiply the distance by 2. Okay, so you are in orbit. Your weight will be divided by 4, so you will be only 100 pounds. Is that clear? But close to the Earth, it's going to be a constant field. So you see those field lines, okay? They are equally spaced out. It's just to show you that the field is constant if you not go far away from the Earth, and it's going to be 9.8. So here, if you take that mass here, you increase its potential energy. You have to do work against gravity. Okay, gravity is very upset, saying, no, 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 that does not work like this. Okay, bring it back. So you have to do work against gravity. You increase the potential energy, which is equal to mgh, right? And it will be acted upon by a force. What's the goal of this force? What that force is trying to do is trying to back, so to lower its potential energy. Very good. So these types of force are called restoring force. Okay, it's when potential energy is involved. So likewise, if you take a rubber band, okay, if you do Pilates, for example, you stretch, 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 and more you stretch, and then you have a restoring force that wants to bring back the spring or the band back to its initial position. So this is called a restoring force. Okay, I'm storing energy because I'm doing work against this spring force. If I let go, all that energy will be released and I get it back. Now, it doesn't matter if I go from here to there. If I go from here, I go for a walk to the library and I go back to the same place. Doesn't matter. So it's not path dependent. So gravity is called a conservative force. Likewise, if you have, for example, two plates here, so this is called a parallel plates capacitor, or just two plates here, you see one is charged positively, one is charged negatively. You're going to have an electric field in between because electric field is trying to bring the plus and the minus together again. Okay, its goal is to lower the potential energy. So it's trying to take this plus, pull it to the minus. It can't because here, if you have like air, it's an insulator. So unless the electric field is very, very strong, and then you have a discharge. So you have like some spark and then current can flow because the electric field is so strong that it's going to ionize this air here. Otherwise, you do have an electric field here. So if you have a plus here, you see that plus here, that could be a proton. And you're doing work, you have to do work against electric field. It's so tiring. Does it have a high potential energy here next to the plus? Yes, because plus and plus, they repel. So what do you think the electric field is going to do? it's going to pull it down, and the force will be QE. Okay? So to visualize that, I thought it would be, since most of you are in the medical field or in biology, you see this is called a defibrillator. And what's happening? One is charged, so you have two conductors. One here, it's positively charged, like the Van Graph, except it doesn't have the same shape, but it's a conductor. So you connect that to a power supply, to a battery. So this is the plus of the battery, this is the minus, connected to the minus of the battery. So this is minus, this is plus. In between, you're going to have an electric field. The electric field is trying to discharge your defibrillator. The electric field goes from plus to minus. It wants to bring back the charge together. And what that happens, if you put that across your heart, and of course the heart and everything inside is a conducting material. Okay, so you're going to have a discharge inside your body, not in the air, okay, because the air is a better conductor than we are. So if the voltage is not too large, you're not going to have a discharge. The electric field is not strong enough to make that combination happen, the plus with the minus. But if it's here across your heart, so you are a conductor, okay, it's going to discharge, and because of the electric field, so you have a surge in current going through your heart. And when that happens, it's the idea is to contract the heart, and maybe it's going to be beating again, and you are resuscitated. But that's the idea of an electric field going from plus to minus. Okay? So the same way, you see, a mass inside a gravitational field will be acted upon by a force equals mg. A charge inside an electric field, and each time you have a charge, you're going to have an electric field. That charge here will be acted upon by a force equals QE. Do you understand? So let's take the defibrillator instead of defibrillator, but it's the same idea. So you remember that's a circuit. I have two plates here. They are both conducting. So it could be a defibrillator. Okay. Defibrillator, you charge it at 100 volt about. So you have a power supply. And as you increase the voltage, what's happening here? You are yes, so you are increasing the charge. Okay, so here it will be Q, here equals minus Q. I can disconnect it, and you see it will stay charged. Between the plus here, the positive plate, and the negative plate, what do you have? An electric field. This electric field is trying to bring all the charges together to combine. Okay, plus don't like to be singles, minus they don't like to be single, they want to be combined together. So that's what the electric field is trying to do. If the voltage is very large, so yes, you're going to have a current flowing between them. Otherwise, it's just stay like that. Okay, so these are called electric field. And you see it's equally spaced. So in that case, the electric field is uniform. Okay, so it's like a magic aura produced by a charged object in such a way that if you place a test charge inside our charge, it will feel a force. And that force wants to bring the charge at a lower level of energy. Is that clear? See, you have the charge here, you can discharge here, right? So this is called a capacitor, but it's the same thing for a defibrillator. Okay, so let's go to the simulation. So I take a positive charge. Now, can you see the aura here all around? This is called the electric field. So that electric field, as you move away, what's happening? Huh? So is it the same magnitude or is it decreasing? Decreasing. Okay. How does it decrease? The magnitude of the electric field at a given point will be the force per 1 coulomb. Okay, so the magnitude of the electric field at a given point will be the force, the electric force per 1 coulomb. It makes sense here. If you go very close, it's going to be pushed away very strongly. As you move away, you see the force decreases. Okay, so the definition for the magnitude of the electric field is the force per unit coulomb. That will be the electric field. So if you want to connect to gravity, so you see F equals what? Gravity mg. And you could define, but we didn't do it. What's the force for 1 coulomb? If the mass is 1 coulomb, what's going to be the force? Let's say we are on here close to the Earth, it will be 1 times 9.8, so just G. Okay, so the force per unit mass is G. So you can see G, which is 9.8, you can see it as an acceleration or Newton per coulomb on Earth. Likewise, if you have a charge in an electric field, okay, the force will be QE. Okay, so E in magnitude will be the force per coulomb. Okay, coulomb, 1 coulomb. So it will be the force per coulomb. So here I have 1 coulomb of charge and you can see that it decreases. Let's find out by how much it's decreasing. So here I have, it's about, do you see that it's 9? Okay, if it was a mass, you multiply the distance by 2, the force, because it's an inverse square law, will be divided by 4. Very good. Likewise, this is Coulomb's law, right? They repel each other. So this is 1 coulomb. It's acted upon by a force, okay, the Coulomb's force. So if you multiply the distance by 2, the force, which is the electric field, should be divided by 4. Let's find out. So 9 divided by 4, how much is 2 point something? 9 divided by 4. 9 divided by 2 is 4.5. 4 point, no, 2.25. Okay, let's see. 1. So this is one distance. Here, you see it's about 2.25 here, right? It's about it's half. Okay, is that clear? So imagine this electric field. You can think of that as air, like blowing out, okay, like a hair dryer. So it's right, you have air being blown away, and if you have a charge here and the charge is positive, it's going to be blown away, pushed away. Is that clear? Now if you have a negative charge, which way it wants to go? Okay, so it does not want to go with the electric field, it wants to go against it. Very good, because the minus wants to go to plus. So remember that typical conceptual equation, a positive charge placed in an electric field wants to ride with the electric field, with the wind. Okay, some people are like that. They like to follow, right? I go with the wind. I'm a positive charge. Now, if you have a negative charge, it's like some people have a critical mind. Yeah, everything you say, they will say the opposite. That will be a negative charge. Negative charge will go always against the electric field. Like salmon, since you are in marine biology, you know, salmon, they go counter stream. That's what they would do. That's why I'm like this. When you tell me to go this way, I will just go the other way. Just because I'm thinking he wants me to go this way, something suspicious there. I just go the other way. So negative charges work exactly the same against the electric field. Now let's put a negative charge now. Now what's happening to the electric field? it's going in. So it's like a vacuum, right? Taking the air in. Now, if you have a positive charge, okay, it's just following the wind. It wants to go with the electric field. So that will be like gravity. If you have a positive charge, it doesn't work the same way because we do not have anti-gravity except for dark energy, but that's another story. But you have two types of charge, negative and positive. Negative, the electric field goes in. Positive, the electric field goes out. For gravity, we have only one type of gravity, okay? It's always in, always attracting. Is that clear? Yup. He say yup, so everything is good. Uh, okay, so a lot of application. An electric field pulls on a charge to make it go faster. The same way that you have the weight wants to bring that down and it's going to accelerate. So how do we produce X-ray? For example, you have a vacuum tube here. So here you're gonna have you connect that to a high voltage, like maybe 50,000 volt. If you have electrons in between, so that will be minus. The minus is here, and the plus is on the other side. So minus, and you have electrons. So the electrons will be accelerated. Okay. So that means I should have placed that picture. It's fine. It's fine. So this is your minus. So it's connected to a power supply. Do you see the power supply here? Okay, and let's say the voltage is 50,000 volt. So you have an electron here. So where is the electric field? Does it go to the right or to the left? This is plus here, this is minus. So an electric field always goes from an electric field. So let's put a plus and a minus here. So now I have a dipole. An electric field always go from plus to minus. Okay, so plus is blowing away and negative sucked in. Okay, so that's from plus to minus, right? Are you with me? I make all those strange noise. So the electric field, which way it's going? Plus to minus. You have an electric field in between the two electrodes. So you have an electric field here, yes? Okay, and now you have little electron because this here is like a filament. It gets very hot, so electrons get free. And do they stay here or did they say, oh, wow, I have plus on the other side, let's cross over, right? So do the electrons go against the electric field or with the electric field? Against. So all these electrons here, they're gonna accelerate, okay? So they will have here, they do have potential energy that will turn into kinetic energy. And all that energy, they're gonna crash here. So this is it's a metallic plate, so it's made of metal, very heavy metal. They crash, and all that kinetic energy is gonna turn into X-ray. You see how it works? Okay? And 50,000 volt. Let's remember the last unit. So 50,000 volt is voltage is a voltage. Remember from last voltage is. Remember, don't erase your memory. Energy per coulomb. Okay? Energy per coulomb. Right? So the potential energy, I'm going to call that delta U, will be the voltage, so for 1 coulomb times Q. Does it make sense? because voltage is energy per coulomb. So if you have Q coulomb, you have that much of energy. Remember from last semester, not last semester, like 2 weeks ago, don't erase your memory, come on. If you have a battery of 12 volts, that will be per coulomb, it's going to be 12 joule. And if you have an electron, it's going to be 12 EV, right? 12 EV, because the electron, so the potential energy will be the charge times the potential from last week. So an electron is E delta V. So that will be a unit. We're going to get back to that, but that will be a unit of energy. So if you have a battery of 1.5 volt, the energy is what? 1.5 volt? Joule per coulomb. And if you have one electron, it will be 1.5 EV. If you have a power supply of 120 volt from the outlet per coulomb, that will be the energy 120 joule per coulomb. But per electron, that will be 120 EV. Okay? That's the energy. It's a potential energy. Okay? So for example, remember, if you have 120 volt from the outlet, that means each coulomb of charge has an energy. But what kind of energy? It's called the potential energy, okay, of 120 joule. 1 coulomb, 120 joule, and then all that turns into energy for the load. Right? Is that clear? Let me ask you something. In an X-ray machine, I'm applying a voltage of 50,000 volts. That will be 50,000 joule per coulomb. But if I have an electron, each electron will have an energy of 50,000 E, because that's the charge, V. Okay, so if you work with an X-ray machine, it would say, okay, it's a 50,000 EV machine, and that's how much energy, okay, will turn into X-rays, 50,000 EV. Do you understand? Okay, don't space out. I see people spacing out here. Don't space out. Stay with me. Stay with me. Are you with me? So for cancer, there is a new, relatively new technology which is called proton therapy. So the idea of a proton therapy is that you take a proton, you accelerate it thanks to an electric field because you apply a voltage. So the proton will be accelerated, okay? And then all that energy will be delivered to the tumor, for example, God forbid, okay? So all that energy will be used to kill the tumor. So it's not everywhere that they use that because it's more expensive. Insurance won't cover it and the all blah, blah, blah. But it's better than regular radiotherapy because it doesn't kill that many healthy cells. Okay, it's less damage, but it's very expensive. So you can look it up. It's called proton therapy. So how we connect that to what we have just said. So proton, okay, is it positively charged or negatively charged? Positive. Okay, so here you have what is called a linear accelerator. So that will be those little protons that you're gonna produce. These are hydrogen nuclei. And here you apply your voltage. So let's say this is plus, this is minus. So the electric field will go to the right or to the left? To the right, very good. And those little protons, they want to ride with the electric field, right? So they're gonna accelerate because of the electric field. So the force for each proton will be QE, which is E in that case. And for that, you need to apply a huge voltage. That's why it's so expensive here. You need to apply a huge voltage of 250 million volt. Okay, so each proton will have an energy of 250 million eV, and all that energy will be delivered to the tumor to destroy the cancer cells. So that's the idea. Okay, so that's why for the application, if you're interested in about cancer, there is a very good professor named Thomas Seyfried. You can find his talk on YouTube. Very interesting. So anyway, let's go back to our business here. So that was just to motivate you. Okay, so one definition of the electric field will be the force per unit charge. And it's a vector, okay? So it has a direction from plus to minus. And the unit will be Newton per Coulomb. Okay, so here it's the same thing. If you have a positive charge, the electric field will be out. Okay, so if you have a negative charge, it wants to go against the electric field. If you have a positive charge, it wants to go in. Okay, here it's the same thing. Okay, so a proton or positive charge wants to ride with the electric field, a negative charge wants to ride against the electric field. Is that clear? So if you put a proton here, is it going to move? Yes, because it will be acted upon by a force. If there is a force, in that case, it will be a constant force, then you do have an acceleration. And you do have potential energy. So it means it's oh my god, my poor notebook. I don't know what was inside. Oh yeah, yeah. So it wants to go from plus to minus, so potential energy will turn into kinetic energy, yes? If you have an electron here, it wants to move. No, it's happy. It's close to the plus, and it's always going against the electric field. So electric field goes from plus to minus. So from here, it could be a Van Graaff generator. Where is the minus? It's going to be very far away. Okay, it's going to be the ground. Okay, far away. I make those noise, but it's weird. Ay, ay, ay. Disgusting. So, by the way, just I was doing this with my other class, but you see those outlets here that you use for the big washing machine or the dryer or the AC unit. Do you see instead of having three, it has 1, 2, 3, 4 prongs here, and you have two hot lines. So one hot line is at minus 120. So see, this is ground level, so minus 120. And the other line is at 120. So what's the difference between 120 and 120? And minus 120 and 120. No, no,
Oh, it's negative. You have to go to zero, and then from zero to 120.
Yes, so how much is that? 240 volt. Okay, so why do we have that? Because that way you have more energy, because those machine consuming more energy, right? Everything with a motor or like I think a microwave also, they need more energy. So they don't want to increase the current, because otherwise, there is a maximum for current, like 15 amp or 20 amps, so they increase the voltage. Okay, so a lot of application in biology. So, for example, any little fish here, because of the muscles that are moving, they're gonna create an electric field all around. Okay, that will look like a dipole. So, what's a dipole? It's when you have plus and minus, like a water molecule is a dipole. These two charges are the same. this is minus, this is plus. So in the water molecule, remember the oxygen takes the electrons away from the hydrogen. So you can have minus 2Q or minus 2E. And here you have 2E. Is that clear? So your two hydrogen gave away their two electrons, and the oxygen here is taking the two electrons. So this is called a dipole. Do you see how the electric field goes from plus to minus, plus to minus? Do you see how it's done? Here going into the minus, away from the plus. So if you have a charge here, it wants to go this way, okay? And here it's going to go in because it wants to follow the electric field. So this is a dipole. So all those little animals and even us, we make electric field. So in that case, because of the muscles, I don't know how it works exactly, but you're going to make like an electric field, like a dipole. And a shark does not have a good eyesight, I think. So it has those, it's part of the nervous system here, and it has little sensors here. And those sensors can detect these electric fields here produced by the fish. And you can even see if it's very close, the electric field will be very strong. It's far away, it's going to be weaker. Okay? So anyway, the magnitude is the force per unit coulomb. You can visualize the electric field. You can even try to do that for a demo. So the way to do that, you get. I mean, you can try. It didn't work with me, but maybe I didn't do it well. But you take castor oil, for example, which is not a conductor, and you have little seeds here inside your oil. And for example, what do you think it's going to be here? So it's connected to a battery. Do you think they have equal charge or opposite charge? It's like, do you think they attract each other or they push away? So do you think the electric field is pushing each other or attracting each other? Okay, let's see. If I take two charges that are the same, do you see how they repel each other? Okay, do you see how they don't want to be close to each other? So even let's do it with 2 plus. That's going to be easier. Don't space out. Stay with me. Okay. Do you see how the electric field is repelling, right? So that's happening here. So this is plus and this is plus. And what you see here, you visualize the electric field. So it means that both electric fields are interacting with each other. So it's like you are trying to bring back a spring, to squeeze a spring, and it's resisting, it's pushing back. So what's happening inside here? So you have an electric field, and let me show you what it really looks like. I think I have it here somewhere. Like this. Okay, so if you have two positive charge, the electric field of each one will interact with each other. And can you see that it's like you try to bring them and they don't want to be together, so they are repelling each other. You see that? Okay, so it means if you have that, and now in the vicinity, so all around, you have little seed here. Okay, is a seed a conductor or a not conductor? A seed like rice, like a piece of rice. It's not a conductor, right? So what's going to happen? It will twist and it will align itself with the electric field. So that's going to be minus, and that will be a plus. How do we call that? Remember? Po, 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 polarization. Okay, it's going to be polarized. Do you see that? It's going to be polarized. So that's how we can visualize the electric field here. Okay, so you have little seeds. Okay, so now what do you think is happening? Are they opposite side or like side? opposite, okay? So this is the configuration for a dipole, okay? So now the electric field is trying as much as its ability, as much as it can to bring them together, right? It's like, I don't know if I have the picture here. You see? That will be the electric field here for a dipole. That was those fishes. That's what they make around them, right? So you have the plus and the minus. So this is like a strange spring. So the electric field is trying to bring them together. Is that clear? So this is the configuration for a dipole. Okay, don't stay with me. Don't space out. Don't sleep. And now you have only one electrode. Let's say it's positive. Can you see here how you visualize the electric field? Do you see that? Okay. And all those little seeds are not conducting. They're gonna twist. They're gonna align themselves with the electric field and they're gonna be polarized. So this is called, could be a defibrillator, for example. So you have two conductors, one is to the plus, one is to the minus, and you can see that the electric field here is linear, okay? From plus to minus, you can visualize it. On the other side, you see it's random. So it means there is no electric field on the other side. Outside, this is called the parallel plate capacitor. Is that clear? So for ideal capacitor, you see there was no electric field here, no electric field here, it's just in between the plates. So that's how a defibrillator works as well. So you see here, do you see an electric field here? So this is, let's say, minus, this is connected to plus. Do you see an electric field? Yes. Do you see how they are aligned? Okay, they follow the pattern. But what's happening inside? Are they aligned? Do you see a pattern or is just random? Random. So what does it mean? It means that inside a conductor, there is no electric field. So it means if you have lightning outside, you stay inside your car, you're going to be safe. Okay, so this is called a Faraday cage. Inside a conductor, you cannot have an electric field. Okay? So important for biology. That's why I'm trying to emphasize the concept. It's the concept the most important. What do you think you're seeing here? Like this little girl, she's isolated. She's isolated from the ground. Okay. What do you think the hair? So hair is not a conductor. It's not conducting. So it's being polarized. And what is it following? What do you see here? The electric field. Very good. Okay, her whole head became like a charged sphere, and you are visualizing the electric field here. Okay, because they get polarized, and she's isolated. So if this is 1000 volts, she will be at 1000 volts. But as long as she doesn't touch the ground, nothing will be to be afraid of. So, for example, if I brought a demo, I don't know if it's working or not. So this is yeah, okay. I could not pay for a big one, so I bought a small one. They have big one, but this one was cheaper. So this is a plasma globe, right? And inside you have a Tesla coil. So it means that even though my USB here will get me 5 volt from my computer, 5 volt DC, okay? With the magic of electronics and a Tesla coil and a capacitor, it's going to raise the voltage to 100 volts. So that little thing inside will be 100 volts. Safe, because it's not the voltage that gives. So if I plug it in, and if it works, okay, sometimes it doesn't work. I don't know if you can you see it? right? You see it? Yeah, you have to, I don't know if I can bring it here. I don't know if it's working because with the lights. Yeah, but it's not. No, I want you to see this. Can you see it? I didn't turn off, but you see? So what is it visualizing here? The electric field, very good. Right? The electric field starts from plus, so let's say this is positive charge inside, and wants to find the ground. So from plus to minus. You see, I hope you can see that the field lines are close to each other to begin with. Okay, that means strong. And then they move away from each other because it gets weaker. So I have 100 volts here, and I am connected to the ground. Do you agree? So my voltage is zero. Okay. So between me and this, you have 100 volt, right? So it should be enough to lit that fluorescent tube here. If you apply a voltage across that tube, you will force the electron to move inside, right? These electrons will kick mercury molecules or mercury atoms, and those mercury it will keep the electrons from the mercury that will be absorbed by the phosphor around here. But you need to apply your voltage, right? Let's see if it works. Can you see? I'm lighting it. So can you see that it's just on one side? It's going to be lit, not on the other side. Why is that? Because my hand is grounded. So the electrons are moving from here back into the ground. It's more impressive if everything that you can see. Can you see that? Isn't that cool? Huh? Isn't that cool? Oh, yeah, even better here. You see that? I don't feel anything. You don't have enough current to kill me. It's not the voltage, okay? It's the current that is dangerous. So you can do that demo as well. Let's go back. I lost. Okay, I lost. I'm lost. Are you lost? Yes, I'm lost. Oh, we have to move faster. Okay. Okay, let's try to do this one. Okay, let's do it. Quick, 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 quick. So the first thing you want to do is drawing. Thank you. Go help each other. Try to do it. More you do in class, less you have to do at home. Blah blah blah. That's why it. Sometimes if there's too much statics, it could be dangerous, right? Because the gasoline can be charged. So we have a small drop of gasoline. So this is my drop. And it has a positive charge. So I'm going to put a positive charge. No, I don't like my drop. I don't know how to make a drop. So this is a drop. This is positive. Okay, we have the mass, and here we have the charge Q. So this is Q. Okay, we have the mass. Okay, the mass 4 times 10 to the negative 15 kilograms. And there is an electric field. So first it says compute the weight. So that's easy, okay? So it means it's going to be acted upon by a force because it's in the gravitational field of the Earth. and the weight will be mg. So mg is easy to find. Okay, so can you do that? So it will be 3, no, just kidding, where's the mass? 4 times 10 to the negative 15, close the parenthesis, times 9.8. Okay, so that will be your weight, the gravitational force. It's a vector. So what you get, very good, Newton. Okay, so there is a weight pulling down. And then it says there is an electric field, but the electric field is up. Okay, so the electric field is up. So there is an electric field everywhere. So it's placed. That little drop here is placed in that electric field here. So we suppose that the electric field is uniform and it's 10 to the 5 Newton per coulomb. So each coulomb will be acted upon by that force. So where is the force? Now it's positive. Positive wants to go with the electric field or against the electric field? With. So it's going to be pulled up. Okay? What's the electric field? Force. The electric force will be QE. Okay, because the electric field is a force per unit charge. So I have a charge Q. The electric force will be QE. So that will be your electric charge, electric force, yes? So what's the charge? 3.2 times 10 to the negative 19. So instead of having a mass, I have a charge. And the charge and the electric field is 3 times 10 to the 5. So this is down. Well, I'm going to put here at down. So that's going to be the electric force is. Oh, I did a mistake before, right?
You guys get it?
3.92. So 4 times 10 to the negative 14. Okay, thank you. And this one is what? Very good. Okay. So which one? Forget about the exponent because it's going to be the same. So which one is the strongest? The up. So this is up and this is down. Is the up larger or the down? So the up is 4 potatoes and the down is 4 potatoes. The up is 9.6 potatoes. So which one is the largest? The 9.6, right? So remember from physics 101 or physics 1, the sum of the force, okay, will be the winner, which is up, minus the loser, which is down. So the equivalent force will be, and you can factor out here, so it's going to be 9.6 minus 4, and I factor out the 10 to the negative 14. So the sum, so the resultant with physics 1, it was called the resultant, will be 5, is that 5.6 times 10 to the negative 14 Newton, yes? Okay, so that's from physics 1. So it's acted upon by two force. If you want to find the equivalent force, it's like someone is pulling with 9 pound and someone else with 4 pound the opposite direction. So the resultant will be 9 minus 4, right? Is that clear? And Newton's second law, what does it say? If there is a net force, I should call it net. Let's call it net equals mass times F equals No, 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 no. Newton's second law. Acceleration. If there is a force, there is an acceleration. If there is an acceleration, that means there is a force. So can you refine the acceleration? This I should call the net. Okay, sorry. You can fix that, especially if you have a tablet. It should be called the net. Up minus down. So you have 5.6 times 10 to the negative 14 equals the mass. What's the mass? 4 times 10 to the negative 15 times the acceleration. Are you with me? So it's going to accelerate up. And if you do that, what do you get? 1.4 or 14? No, 14. Why is it 14? Are you sure it's 14? 5.6 divided by 4? It's 14? I don't know, but why do you have a 10 to the negative 15 down there? It's not 14. It's 14? 14. Oh, yes. Oh, it's my fault. Oh, thank you, thank you. It's 4 times 10 to the negative. No, 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 it's not my fault. It's your fault. No, I mean, you are right. Sorry. So 15. Okay, and I didn't do it right. So what do you get? 14. So acceleration will be 5.6 times 10 to the negative 14, you are right, divided by, open the parenthesis, 4 times 10 to the negative 15, and you get 14 what? 14 cookies, 14 what? What's the unit? Very good, okay? So it means every second it's gonna go faster by 14 meters per second. Okay, are we good? I have another visualization before we move on. But of course, I lost my film. Uh, so what you see here, you see the Van Graaff, you see the Van Graaff generator. Okay, do you see how it's producing an aura around it? So this is called the electric field. Okay, so very far away, it's gonna go into the ground. And inside that electric field, I'm going to place a small charge, small enough that it does not, although it does disturb a little bit the electric field here, so it's small charge here. Do you think they are opposite or equal? Or opposite or like charge? What's happening here? Are they attracting each other or repelling each other? So wait. Now. So they are attracting each other, right? So the charge will be opposite. Now if I have like this one, like here, and now what are they what? Repel each other, which means they are same charge. Do you see how it's not really the charge interacting with each other, but they interact through their electric field? Very important for biology, by everything electric field charges. Let's see if I have something else. You see, they attract each other, but this one has enough momentum that it will not crash on that one, right? It will just pass by. Likewise, if you have like a comet and this is the sun, they're gonna interact with each other through their gravitational field. Do you see? Can you visualize that? So that's how it works. Okay, the rest is a review. So the electric force, like the electric field, is follows an inverse square law. So here, if the distance increases by a factor of 2, so it means the distance is multiplied by 2. So the force of the electric field will be divided by 4. Very good. It's an inverse square law. Okay, so for example, if they were 10 centimeters apart and now they are 5 centimeters apart, so what's happening to the distance? It has been divided by 2. So the force is multiplied by 4. So the answer will be A, right? So this one is, what do you think? Electric field, okay, by definition, is the force for 1 coulomb. 1 coulomb in an electric field here will be 10 Newton. So if you have 5 Newton, what's going to be the charge? Yes, it will be, no, so here, for 1 coulomb, you have 10 Newton. So half of a coulomb, you're going to have 5 Newton. So the charge will be 0.5. Let's find out if it's up or down. So if you want to do it, you don't have to do it in your head. You can say, okay, this is the electric field. Okay, this is the force, and you have F equals QE. So the magnitude, okay? So if the force is 5, E is 10, so Q will be 0.5 coulomb. But this is in magnitude. Let's see if it's positive or negative. Okay, where is the electric field? Up or down? Okay, so up. And it says that the charge here will be acted by a force which way? Up or down? Down. So that means that charge is negative or positive? Which one wants to go against electric field because they have such a negative mind? Negative. So negative charge go against the electric field because they have a negative mind, and positive charge goes with the electric field because they have a positive mind. You know, they are happy and they say, whatever you say, I follow you. They are followers. Negative charge have a negative mind and they go against the electric field. Is that clear in your head? Typical conceptual question. A negative charge goes against the electric field. Why is that? Because look, positive, an electric field goes from plus to minus. So you see the negative charge wants to go this way because it wants to go to plus to decrease its potential energy. It makes sense? Yes? Okay. So for a point charge here, you see the electric field here, it's like an aura, blown, pushed away. You see those lines here are close to each other. That means the electric field is very strong. And as you move away, the electric field is decreasing. Do you agree? Ah, I lost everything. I lost all my demo. I don't know. Shall we drop this? So do you see that the electric field is decreasing? Yes. Decreases by a factor of 4 because it's an inverse square law. Talking about inverse square law, you see, The electric field is the force per unit charge. You see how it decreases? And we just show that's an inverse square law, yes? Remember I showed you that? Okay, so it means if you have a distance here and the electric field here is about 35, you multiply by 2 the distance, then it's going to be divided by 4. Okay, so 35 divided by 4. So that will be the equation for the electric field. Okay, so the electric field will be the force per unit charge. So you take your Coulomb's law and you replace one of the charge by 1 Coulomb. Is that clear? So at a given point, if you want to find the electric field here, so let's say at a distance r, so that will be a distance r, I don't know, make a distance r here, so that will be the distance r, okay? It's going to be acted upon by a force here, because if it's positive, so I have 1 Coulomb of charge, okay, it's going to be pushed away, yes? So the force on that, and that will be BQ here. So the force will be equals to K BQ times 1 Coulomb over the distance square. And that will be the definition of the electric field. The electric field is the Coulomb's law. Okay, you apply Coulomb's law, the Coulomb force, for 1 Coulomb. In that configuration, that will be the electric field. You see the electric field is decreasing as a square of the distance. That will be for a point charge. Is that clear? Yes? Interestingly, if you have like Van graph, so I want to show you why Van graph are not deadly, except maybe if you have a pacemaker, something like this, maybe not a good idea, but otherwise it's safe. So first of all, let's say your Van graph is positively charged, yes? So do you see that the electric field is away, right? Let me ask you something. And do you see that the electric field is always perpendicular to the surface because it's a conductor? So this is perpendicular, this is perpendicular. Can I have an electric field inside? No, very good. No electric field inside the conductor, right? And you can apply exactly the same equation. So that means, let's say the radius here is r. So that will be the radius of your Van graph. Inside, what's going to be the electric field, we said? Inside the Van graph, it's going to be, can you have an electric field inside the car when there is lightning? 0. The electric field just happened here at the surface, and it's going to decrease as the square of the distance. And here, everything happens. So let's say you have a charge Q on it. So this is positively charged. Okay, so it's 1 proton plus 1 proton. So 1 proton, so it's quantized. The electric field will be K and Q and the distance here square. At a distance from the center at a distance r, you're going to have this electric field here. Yes? So let's suppose that you have an electric field at, like you have a Van graph, let's say at this distance here, at that distance here, so at a distance of 50 centimeter, if the charge here, if the charge is 5 microcoulomb, so you see it's a very little charge. That's why it cannot be dangerous. You cannot have a lot of charges here because of the geometry. They repel each other. There is so much that you can put in there. At some point, no more. So it cannot kill you. Can you find the electric field here at a distance of 50 centimeter? So we suppose the size is smaller than 50. So the electric field will be, you can imagine that the electric field will be the force per unit coulomb. Okay, so it means you have 1 coulomb of charge here. It's going to be repelled. What's going to be that electric field here? Is the force per unit charge. So it's going to be what? 9 times 10 to the 9. The charge on your Van graph is microcoulomb, and the distance between here and there, it's going to be 0.5 square. So what do you get? I see people staring. Why don't you do it? Why don't you take a calculator and do it? So you are saving time, so you don't have to do it at home. So what you get? 11? No?
Maybe you put it wrong, but I got a bunch of zeros, but 1.8. Let's turn this side direction.
So 1 times 10 to the 4? No? I did a mistake. 1.8 times 10 to the 5? Okay, let's see. 9 times 10 to the 9 times 5 times 10 to the negative 6 divided by 0.5 square. That is 1, 2, 3, 4, 5. Did you get that? Okay. So again, the electric field at a given point in space will be the force per unit coulomb. So it means you place 1 coulomb here and you find out what's going to be the charge, the force acting on it. And we already know Coulomb's law. Is that clear? But now I'm trying to trick you. And now I say, what's going to be the electric field at the distance of, so let's say this is 20 let's say the radius is 20 centimeter. Yes, you with me? Okay, what if I ask you to find the electric field at a distance 10? To trick you. So some people will just jump on the equation. So wait here at a distance of 0. So 20 centimeter is the size of your Van graph. Now I'm asking you the electric field for a distance equals 10 centimeter. How you do that? Do you jump on the equation or you think? What's happening inside a conductor? No electric field. So if I try to trick you, remember, because I know half of the class will not get it right, they will do this, okay? Equals to 0. Inside the conductor, the electric field equals to 0. Okay, and if you go back to the visualization, here, you see, this is a conductor. It's being charged because it's connected to a plus or a minus. Inside here, you see all the seeds here go in different direction. There is no electric field inside here. So let's say this is plus, electric field wants to go to minus, that will be minus, so plus to minus, you do have an electric field, but inside a cage. So this is called a Faraday cage. So that's why if you are taking your car, driving in a tunnel, for example, you are losing signal because the electric field cannot penetrate a frame, like a metallic frame, cannot get inside. So don't so here, you see, if you go to Boston, they have a science museum. So he's inside a cage. He's not afraid. except for the noise. So it's a lot of noise here. So it has like an earplug here, but there is a breakdown. So you see the electric field here because the cage here is connected to the ground. So if this is positive here, you see electric field wants to go from plus to the ground. So you visualize the electric field. The voltage is so large, thousands of volts, that will be enough to have a breakdown. You have a discharge, and the charge wants to go to the ground. Is he safe inside? Yes, because the electric field cannot penetrate inside the cage. Okay, it's called the Faraday cage. So it could be the chassis of your car. Same thing here, okay? But you can check your phone, you won't get anything, you cannot get a signal, right? Because of course, a signal is made of an electric field. So if the electric field cannot get inside, you won't get any signal. Well, will be very bad. Very good. Okay, that's why he's holding his hand here along his body because if he touches, that's it. Okay, he's dead. Now, I don't know if he's dead or not because I don't know if you have a lot of current, but no, not a good idea. Okay, so that will be the equation of an electric field produced by a point charge. Okay, you have other equations for different configuration, but that's the simplest one that you can have. That will be the electric field at a distance r from the point charge, as you are just using Coulomb's law. That means the force for 1 coulomb. For a point charge, it will have this equation. Is that clear? Okay, magnitude. Okay, let's try to do this one. Okay, let's test your algebraic skill. Let's test algebra. So you have you see here you have a positive charge, and here you have another positive charge. So now you have a distribution of charges, right? One positive here, one positive there. Can you see that this one is stronger than that one, right? So does it make sense to you that at some point, so let's see, I take a strong charge, so now I have two, I'm going to add here, two here, add another one, so I have three nanocoulomb, for example, and here I have 1 nanocoulomb. Now, can you see that here it's going to be pulled, pull. Oops! You see that? What's happening at that point here? What's going to be the net force? 0. So at that point, the electric field will be equals to 0. The electric field is a force on 1 coulomb. So this is 1 coulomb. It's going to be pushed to the right, pushed to the right, pushed to the right, and here it's pushed to the left. And just right there at that location here, it's hard to get it, but you see there is no force here. Here, almost got it. But right there, it's going to be 0. So at that location here, there is no more electric field. Yes? Okay, so now that you get the idea, find that location here where the two electric field will cancel each other. So we use the superposition principle to find the electric field at that point. We're gonna add the electric field. So it's like finding the net force. Find the net force on 1 coulomb. So you want to find that location here when the force from this one will be equals to the force to that one, and they cancel each other out. Do you understand what to do? So the net electric field here will be the electric field produced by Q1 plus the electric field here produced by Q2, and you add them up. And they cancel out. So E2 equals E1 if they cancel out. So you are finding D, that distance here. You are finding that distance here where they cancel out. So if I go back to here, you see the electric field here is the sum of the two electric fields from the left and to the right. And here they cancel each other out. What are you looking for? This distance here. Do you understand? Is the question is clear? Okay, don't stare. Stop staring. It's scaring me if you stare like this. Do it, do it. At that point P, okay, you're going to have an electric field from Q1 and you have the electric field from Q2. And in that case, they cancel each other. So Q1, E1 equals E2. So find that distance here. Okay, so use that equation here, that formula. Okay, you can do it. That slide, by the way, comes from the book Johnson and Cutnet that I was recommending. Come on, you can do it. Can we do it? Yes, we can. Do it, okay? Don't stare. So E1, the electric field due to Q1, okay, have a 1 coulomb. It's gonna be K, okay, Q1, okay. The distance, so on the denominator, that will be the distance between the source, and where you place your 1 coulomb. So that distance will be G squared. Do you agree? Okay, and then E2, I'm talking about magnitude here. E2 will be to the left, but it's going to be K. And then here you always have the source of the electric field, which is Q2. You can put a 1 coulomb if you want, times 1. And then the distance between the source and the point, what's that distance here? Because I have 3 and I want D in my equation. So that distance will be 3 minus G, okay, or you call it R, you can square, okay? And physics stops here. Math takes over. E1 equals E2, okay, so you have K, okay, times Q1 is 16 micro, okay, there is a micro here, times 1 over D square equals to Q2, which is 4 micro. Come on, you can do it. This is math, okay? That's not a physics class anymore. This is just math. You have a K here, K here. What do they want to do? Very good. Go bye-bye. You can do the same thing with the unit. So you have a micro here and a micro, so they go bye-bye. Yes, you can divide both on the 4 on both sides, but you see that there is a square. Yeah, you can divide on both sides by 4. And then what can we do on both sides? You take the square root. So the square root of 16 is 4 over D equals the square root of 4 is 2 over 3 minus D. Much, much better. And then you can cross here equals cross there. See? 4 times this equals that times this. It's a proportion. Okay, so you can do 4 times 3 minus D equals 2D. No, I didn't. No, that's right. 4. I did a mistake somewhere, no? Uh, 16, 4. Okay? Okay, you can do that. You expand. So 12 equals 6D. So D equals 2. No, simple. How do we call that in math? You. So this is okay. That could be cross multiply, but this is called you distributing. You distribute one for you, one for you. Yes.